Welcome everyone. This is 10th week we are meeting, and as usual, we will start with recalling what is done in this week, and then we'll solve some simple questions. Uh, okay, so let's begin. Okay, so in the week 10, we were actually studying about inner product spaces. Okay, we started inner product space in ninth week, and in this week, we have progressed along these lines. Uh, this is definition for best approximation of a vector V to a subspace W. Okay. So given any element of vector space V, which is in inner product space, what is best approximation of beta by the vectors of subspace W is actually alpha of this type. Means distance between beta and alpha is the smallest distance. Okay? In this sense, if mod beta minus alpha denotes distance between B and beta and alpha. So alpha is the unique point where we have beta is the smallest point as it was discussed in the class. So I suppose you understood this. Like if you have 3D, let's say three dimension R3 space. Let's say it is R3, and if you take some point X, Y, Z, it was given in the classroom. So it project it down to XY axis. If it is your survey space, let's say uh, this XY plane, this is your subspace, let's say W, then project it on. This is your alpha, XY0. Okay. So alpha is the nearest point at beta. Okay. That is why we call it best approximation. Okay. So let's say next theorem, which is saying if V is an IPS means inner product space, and WB subspace, okay, of V, and beta is any element of V, then we have the following three statements that alpha is best approximation of beta, then beta minus alpha is orthogonal to each vector in W. For example, you see here this vector beta minus alpha, this vector which is parallel to, let's say, z axis. This is your z axis. This is orthogonal to each vector. Take any vector inside this plane, xy plane. They are in 90-degree angle with the z axis. Okay, like that. So beta minus alpha is orthogonal to each vector inside W. Next statement is that if best approximation of beta exists, it is unique. Okay, so we have a unique point which is nearest to V inside W. So if dimension of W is finite and alpha 1, alpha 2, alpha n is orthogonal basis of W, then any sorry alpha alpha can be taken as just projection onto these coordinates alpha i's. Okay, like what I did here in this case, 1 0 0 0 1 0 was orthogonal basis. I have projected into first coordinate, means x axis. If it was your e1, so this is written like summation beta, which is xyz, with e1 taking inner product is giving you x in the first coordinate, so you multiply with e1. Okay, let not write some, plus you have second basis element, which is e2. You are just projecting inside uh, second basis vector. Okay, why I'm not writing mod e1 square, because that is 1 here. Okay, in this case mod e1 is just 1, so 1 square does not make sense. So this was your this sum was equal to x y 0. Okay, check it. So then you will understand this statement. Okay, so it is unique in the sense you got the coordinates given as coordinate of a vector, you get a unique vector. If you know the coordinate, that is the unique point. Okay, denoting alpha. Okay, so here we have Bessel's inequality. It says if V is an inner product space and we have orthogonal base, no, no, set of orthogonal vectors, okay, and beta be any element of V, then we have this inequality. Okay, if you understand it in R2, what it represents, it is just triangle inequality. I think. So if you have a plane, let's say you call it R2, okay, and take any point x, y, and you have orthogonal vectors, let's say E1, E2, then what is this? This is projection onto x-axis. This quantity is just this vector. Okay, length of this vector. Sorry, length of this vector. And what is this one? This length to this. This is your second when you take k is equal to 2. For k is equal to 1, for k is equal to 2, you get this. And what mod beta square is? This. This is Pythagoras theorem, right? Okay, in this case, they are equal. It can have, this could be equal in finite dimensional spaces. Sorry, finite dimensional spaces, but it is not always true. Okay, so this, if your space is finite dimensional, this is correct. They both will be equal, but for infinite dimensional vector spaces, there might be this kind of inequality. Okay, so this is just Pythagoras theorem, in fact, nothing else. Verify it. Uh, okay, let's say next. This is generalized Pythagoras theorem. Okay, for higher dimensions. For finite dimensional, this equality occurs. For infinite dimensional, it can happen that uh, okay, this is equal if and only if this alpha is alpha 1, alpha 2, alpha n is a basis, is a basis of V, then equality occurs. Okay, so I'm leaving this by this. You read about it more from the book you have. Okay, so corollary. Next corollary is let V be an inner product space and W be finite dimensional subspace of V. E be the orthogonal projection of V on W, then mapping which associates each element of V to an element. If it was beta, then beta minus E beta. This is orthogonal projection of V on V W orthogonal complement, or let's say W complement. If I say it is orthogonal complement, okay. But how W orthogonal complement is defined? This was defined those vectors inside V such that V inner product with W is equal to 0 for every W inside this W. Okay. So this was also coming out to be a subspace of V. Okay. Now if you have E projection, orthogonal projection on W, then what it says that I minus E, this is orthogonal projection on W complement. This W orthogonal complement. Okay. So this was also proved in the class. So that's why I'm leaving this. So this might be used in exercise. Okay. Am I audible, right? Okay. So
Yes, sir, audible.
okay. Okay. Thank you. So let's say next theorem. It's also about inner product spaces. We have W as a finite dimensional subspace of V, and EB the orthogonal projection on W. Then each okay. By the name itself, it is a projection. So it is an idempotent operator. Okay. All projections are basically defined like this. That T square is equal to T, then T is just projection map. Okay. Projection onto its range. But here range we have is W. So projection onto W. So we have null space of it just this. Uh, all those vectors which are orthogonal to W. Because this is orthogonal projection. By the name itself, it is clear. Like. So in this theorem, we are using this uh, corollary. Okay. I minus beta is orthogonal projection onto V transpose. Sorry, V complement. Sorry, W complement. And then V can be written as direct sum of W plus W complement. And direct sum itself represents that nothing is in intersection, non-zero. Only zero is in intersection. Okay. So I suppose you understood this. So I'm leaving. Okay. If you want more explanation, I can give you like for any V you can write E beta, which is projection onto W plus sorry EV I minus E of V. This equality agas right? EV get cancelled from it, and but this belongs to W transpose or W complement. That's all. By the above lemma or corollary. It was a corollary, yes, and it belongs to W because it was projection onto W. E was projection onto. So that's why this can be written as linear sum, but it is direct sum. Why? Because if V belongs to W intersection W trans W complement, sorry, then V itself V orthogonal to is itself. Okay, but this will imply that inner product property has this property that this V V inner product with which V itself is positive. If it is zero, it means V is itself zero. That's why only zero is inside means common. Okay, zero is inside intersection. So let's say next theorem. I'm just recalling so that we can directly apply to the questions. So you should also read once so that it remains with you. So let V be a finite dimensional inner product space. F be linear functional only. Then this is called representation theorem. Okay. I think Rees representation theorem was something like representation theorem. Basically, every linear functional on V that can be written as this inner product with alpha beta. That there is unique vector beta which represents F. Okay. And what is that unique vector beta? That is actually this, defined like this. Okay. And in the class, it motivation was given why we are taking this to be beta. Okay. First of all, this beta works, and then how we guessed this should work. So this was given in the classroom. Okay. So go and watch it if you want to read it once more. Maybe you want to recall things. And the next thing is defining adjoint of is a linear operator, is a linear transformation from V to V itself. Then we define transpose of adjoint operator of V like this. So if you define F alpha is equal to V alpha beta, beta is fixed. Let beta belongs to V. Then this was linear functional. This was linear functional. So this can be written as alpha beta prime by representation theorem. Okay, Reed's representation theorem, whatever from this above theorem. Okay, so there was beta like this. So I'm writing beta prime here. So given any beta, this beta, you got beta prime here. So that your linear transformation, which is given by T alpha comma beta in a product. So this is equal to, so unique beta prime. I'm writing T star of beta. Okay, T star of beta. It depends on beta. That's why I'm writing T star of beta here. So this is defining property of adjoint operator. Okay. So this is how it was defined, and then this was matrix representation. So it was T star. It was also proved that T star is a linear operator on V. This was proved. So let's see next. This was matrix representation of T star. So V is a finite dimensional inner product space, and we have bases like this: alpha 1, alpha 2, alpha n, orthogonal basis, ordered basis. So T is a linear operator on V. Then if we have matrix representation for T with respect to this orthogonal basis of V given by A matrix, this is your matrix. Then kjth entry of A matrix. This is given by this. Okay. And one more thing, that T star, if T star is given by B, then B is nothing but conjugate of matrix A. I mean, first you switch the order of JK, make it KJ, and then take complex conjugate of it. Okay. So something like, if you have matrix representation like 1i 2 3, then if it is A, then I'm right. A conjugate is nothing but 1 minus I 2 3. Okay. So first of all, I'm taking transpose and then complex conjugate of it. That is what is written here. It, so I'm leaving this. It was proved in the class. And last one more thing to recall is here. Let's say this is some corollary, maybe some proposition. Like if you have 100-dimensional vector space and is an orthogonal projection on some subspace W, then its adjoint is equal to E itself. Okay. So can someone recall this, or we should go? So first of all, V is written like W direct sum, W trans W complement. Okay. Any V can be written as E V plus I minus E. Remember, I minus E was the projection onto V complement. Sorry, W complement from above, if you remember. So this belongs to W, and this belongs to W complement. So I'm just trying a, or I will leave it. EV W is equal to, in place of EV, we can write V minus uh, from here. Okay, from here you check. In place of EV, we can write IV minus I minus E V comma W. So in place of W, you can also write. So let me replace it. IV minus I minus E V in place of W. This is IW. Okay, identity applied on W. So I minus EW plus EW. Okay, so nothing changes. But if you remember, this is orthogonal projection. Sorry, I minus E is orthogonal projection on W complement, and E is projection on W. So whenever they get in composition, that will be equal to 0. So, so here what remains is this. Here you have IV, and this will go to this, and this will become 0. IV with I minus E W plus, some calculation. Okay, this will be like, after some calculation it will be like E W. Okay, so in that case, so there, after some calculation it will be like this. I will do it in coming exercises maybe. So I'm leaving for maybe half an hour. Then I will do it. Okay. So here we get unique vector that was E star of W. But we see here from comparison we get E star is equal to E. Okay. So let me see. Uh, I'll do it in coming exercises. I think this is given in some exercise. So let's see now question. V's are three standard inner product. Yeah, standard inner product on R3, and this is a given vector 10 minus 10 2 5, and this is given subspace W. X XZ type elements. Then best approximation of beta by the vectors in W is, you remember one thing, if you have alpha 1, this is two dimensional. Okay, first of all, dimension of W is equal to 2. If anyone has doubt, means have doubt, you have doubt, you can ask. Dimension of W is equal to 2. So we can get a orthonormal or orthogonal basis alpha 1, alpha 2. Okay, this is basis for W, orthogonal. This we can find a orthogonal basis. Okay, why? How? We have a process in the last week. There was a process, gram is with orthogonalization process. So any basis can be transformed into an orthogonal basis. Okay, so we have orthogonal basis for W, like let's say alpha 1, alpha 2. Then we just look at theorem or corollary here, here, from here, here. Yeah, best approximation is unique. Alpha is given by this inner product, and then this is just projection onto alpha is coordinates, and then the sum. Okay, so let's see. So let me write formula. We want to calculate best approximation. Let's say alpha. This is nothing but beta alpha 1, alpha I, alpha I direction mod alpha I square. This is inner product. Okay? I equal to 1 to 2. So let's write beta is equal to minus 10 to I inner product with alpha I. So first of all, we should get a orthogonal basis for W. So I'm just taking 1, 1, 0. This is your alpha 1. Take alpha 2 is equal to 0, 0, 1. Now, is this orthogonal basis? Is this orthogonal basis? Yes, it is. So standard inner product, what is standard inner product does? Coordinates wise multiply and then take sum. So coordinate wise multiplication will give 0, 0, 0, and then sum is itself 0. So inner product of alpha and alpha 1 and alpha 2 is 0. So they are orthogonal. Okay. So 1, 1, 0 is inner product in this direction. 1, 1, 0, 5 mod of norm of 1, 1, 0 square plus one more term is left, minus 10 to 5 1, 0, 0, 0, 1, sorry, 0, 0, 1. Norm of 0, 0, 1 in this direction only, 0, 0, 1. So how much is this? Minus 10 plus 2, 5 becomes 0. Okay, so no worries. 1, 1, 0, 5. This is inner product of this vector itself. So 1 plus 1 is equal to 2 plus. So if you remember this formulas, x1 comma x2 comma x3, norm of this is nothing but x1 square plus x2 square plus x3 square. Okay, so that is how we got to here. 1 square plus 1 square is equal. And here we have 10 into 0 becomes 0. 2 into 0 itself 0. This is not 25. Okay, this is 2. This is looking like 3. So this is 2 comma 5. So we got 5, just 5 left in third coordinate. 5 into 1 is just 5. Below this is just 1 square is that 1. In direction 0, 0, 1. How much is this? This is minus 8 by 2. 110, and this is 5001. Now this is just minus 4, okay, minus 4 comma 0, and here we have 005. So we have minus 4 and 5 in third quadrant. So this is your best approximation to W of beta. Okay, minus 4 and then 5. This option is
Excuse me,
right.
sir.
Yes.
Sir, here orthogonal basis is required or orthonormal basis?
So if you take orthonormal, then this part, this denominator part, you can remove it. Okay. So orthogonal will work if you write your formula like this. Okay.
Okay, okay,
If you take orthonormal, then remove it basically.
okay.
Good. So let's see next question. V is R3 and W is subspace given by elements of the type X, Y, Y. Then orthogonal projection of V on W is given by. So if there was just a vector, let's say W is spanned by uh, alpha 1, then for any vector I will write, let's say V projection onto alpha 1 in the direction of alpha 1, and then I will take norm alpha 1 square, so that if alpha 1 was not unit vector, then I will take, means I will divide by alpha 1 square, so that it will become a unit vector. Okay, it will work as a unit vector. Why? Because the same thing can be written as alpha 1 by norm alpha 1. So this is now unit vector, this vector, and here also alpha 1 by norm alpha 1, this is also a unit vector. Okay, so that is why dividing by alpha 1 square is working. So but anyway, alpha 1 is non-zero. You know why? Because it is a basis vector. So we can take norm of alpha and divide by itself. Sorry, by it. So this is good. So let's see. So if we have more basis vector alpha 1, alpha 2, then projection is calculated like this formula. Okay. Best approximation projection is nothing. Orthogonal projection is nothing but taking best approximations. Okay. So take general element x, y, z. Okay. First of all, let write a basis for it. W, beta W, which is we want orthogonal. So because it is R3, it is supposed that inner product is standard inner product. Inner product. Okay. So that this 100 and 011, this becomes orthogonal basis. Okay. Is orthogonal base or W. Sorry. Okay. So now we just use these calculations and we'll get it. X, Y, Z, inner product with 100, and the norm will be 1. Okay, so that's why I'm not writing 100 plus, this is your orthogonal projection, let's say denoted by P of X, Y, Z. So here it is written by E. So let me write by E. E of X, Y, Z is equal to this. Now same X, Y, Z inner product with 011 in the direction 011, but this was not unit vector. Okay, that's why I'm going to divide it by how much? 1 square plus 1 square, that is 2. Okay, directly writing like this. So this was nothing but norm of 0, 1, 1 square. Remember that. So how much is this inner product? This is your x only in the direction 1, 0, 0. In the second, you got uh, y plus z. Okay, first coordinate becomes 0, so that's why not taking part in the sum. Need below we have 2 in the direction 0, 1, 1. So what we got? X from first coordinate. Second and third is same, y plus z by 2. Okay, so I think option A is correct. Yes, yeah, option A is correct. If you have doubt, you can ask me. Okay, otherwise I will go to next question.
Repeat, sir, one more times.
Okay, so if if we have a vector and we want to project some other vector onto the line given by this unit given vector alpha 1, so the projection is like if you have this alpha and expand it into line. Okay, this is your now subspace, let's say w given by alpha 1, and take some other point v. Now let's say this is your 0, 0 vector, means identity of the vector space. If you want to project this vector onto this given vector orthogonally, so you want best approximation by this point. This point is also a vector in the direction of alpha 1. How to calculate this projection vector? Take inner product of alpha with, sorry, v with alpha 1 in the direction of alpha 1 and divided by norm alpha 1 square. So that this is just explanation why we are, if we have unit vectors, then we just take inner product in the direction of and then multiply with the direction alpha 1. So if it is not unit vector, then we have to divide it by normal alpha 1 square. So this is how we calculate it. So now best approximation. If we have more vectors, let's say beta w has a more vectors, let's say this vector and this, they are forming orthogonal basis for w. Then best approximation can be calculated like this. First take inner product in the direction of this vector, and then inner product and and this vector 0, 1, 1 with this quantity. Okay. So I'm writing here in the denominator norm 0, 1, 1 square. Why? Because it is not unit. In this case, I'm not writing because this is just one. Now, inner product is a standard inner product. So inner product in first we get x, and in the second you get y plus z. Now we have x by 1 here, y plus z by 2 here. So now it is just calculation. So no need to explain. Okay, so remember this best approximation formulae. So I think you understood, right? Okay. So let's see next question. Given an inner protected space, which is again R3, everything is in R3. This is right. So equipped with a standard inner product and subspace W uh, of B, and this E be the projection, orthogonal projection of P onto W. Then the projection, orthogonal projection of B on W complement. Okay, so you remember this I minus E will work as So if you remember this, everything is simple. Now just calculation you have. So let's say matrix representation of E with a standard basis, standard ordered basis. Okay. Let me write first B. Take B to be 0, sorry, 1 0 0, then 0 1 0 0 0 1. This is your standard basis, ordered basis. Then what is your E beta? First column will become 3 1 minus 1. Or from here you write directly like 3, sorry, minus 3 1 0, then 1 0 4 minus 1 1 0. Okay. So I'm writing it directly, but how to you write it? You just take E applied to E1. This is your first column, and but what it is? Minus 3 1 minus 1. Take it, and E2 is nothing but 1 here, 0 here, 1 here. Sorry, 1 here. Sorry, we are just putting y is equal to 1 and everything else is 0. So I'm wrong. Okay, putting y is equal to 1 gives 1 0 1. Okay, now putting matrix representation is wrong. I'm coming to that. What is E of E3? Just putting z is equal to 1 and everything else is 0. You get 0 here, 4 here, then 0 here, right? Am I correct? Someone correct me.
Correct, sir.
So here we should get 1 and here 0. Here we should get, sorry. This is your first column, 3, 1, minus 1, nice. 1, 0, 1, this is your second column. 0, 4, 0 is third column. So I was correct. Sorry. So this is your third column. I just think this is third row. Yes. So that is why it became chunk. Now this matrix representation is correct. Okay. So now what is I minus E? I is matrix I has matrix representation 1 1 1. 0 here, 0 here, 0 here. Minus E has a matrix representation minus 3 1 0 1 0 4 minus 1 1 0. So you should remember these things. T1, uh, if it is composite T1 T2, then matrix representation becomes uh, matrix representation matrix multiplication. Okay, T1 T com- T2 T. But if it is sum T1 plus T2, then it is matrix.
Sir, good evening, sir. We cannot see, sir. It's not. Sir, excuse me, sir.
My screen is my screen
Sir,
off?
excuse me, sir. Amen,
Yes.
sir. Yeah,
Tell.
yeah, it is not visible.
Might be your
I didn't
internet issue.
see your writings, no?
It's visible here. I think it's your connection problem.
You can rejoin. Okay. Leave this meeting and join it again. That will work, I think. Okay. So let's see. So this is just to remember this, or you should practice it. Okay, calculating matrix representation of T1 plus T2. This will be the sum of the matrices T1 and T2. Okay. So here we have matrix representation of I minus B, sorry, I minus C. It is standard basis. This is nothing but this. So what it is? 1 minus 3 becomes plus 3 becomes 4. 0 minus 1 becomes minus 1. Now it is 0, 0, 1 minus 0. Sorry, here we get minus 1. 0 minus 1. 1 minus 0 becomes 1. Little mistakes are happening. So here, okay, 1 plus 3 becomes 4. 0 minus 1 become minus 1. 0 minus 0 is 0. Now 0 minus 1 is minus 1. 1 minus 0 is 1. 0 minus 4 is minus 4. 0 minus 1 is plus 1. 0 minus 1 is minus 1. 1 minus 0 is 1. Okay. Now you have this matrix representation. Just writing in expressions, you just have to multiply it by xyz, where xyz goes. Okay. So let me not write here. I'll cancel it. I minus E. This is your projection onto W complement. How to write it? It is given by M. So let me write it by M. Okay. Then M of xyz. This is I minus E applied to xyz. And what is it? This matrix representation you have 4 minus 1 0 minus 1 1 minus 4 1 minus 1 1 applied to xyz, and you get 4x minus y. This is your first coordinate. I'm writing in row so that it matches with representation. Okay, you get a column, but let me write like this. Okay, so you get minus x plus y minus 4z. This is 4. Okay, so you get x minus y plus z. Okay, so this is your M projection onto W complement. Let's see which option is working. 4x minus y. So this is fails. This fails. This. Next one is x minus x plus y minus 4x. Minus x plus y. Minus x plus y. This fails because it does not have minus x here. Minus x plus y minus 4z. Right. Now last coordinate is x minus y plus z. X minus y plus z is here and not here. So this fails. This is okay. So this looks lengthy, but it is simple, right? Just if you know what is orthogonal projection on W complement given by I minus A basically, then it is simple. Okay. Mosquitoes here. So let me go to next question. I think you understood this. Okay. Let's see next question. We have again R3. Inner product space is now different, given by this um, specially defined inner product. The P linear functional given by this 3x plus 4y present. Then the element beta, which represents f. What is it? This? So I think this would be simple. Let's say beta is let's say beta is just x1, y1, z1. Then alpha to some random element, let's say x, y, z. Alpha is just x, y, z, general element, arbitrary element. Now, uh, alpha, beta, inner product. What is this? Specially defined inner product. Remember this. 2x, x1, right? Plus 3, y, y1, plus 4, z, z1. Okay. Now, what is f alpha? F alpha is just given by 3x plus 4y plus z. So we want these to be equal, but this equality condition will imply that 2x1 is equal to 3, 3y1 is equal to 4. Just compare here. Okay. So 4 z1 is equal to 1. X1 is equal to 3 by 2 will work. What? This is just guess, okay? Some kind of guessing I'm doing here. 4 by 3 here. Z1 is equal to 1 by 4 here. Because if we take Z x1, y1, z1 this, so this is if and only. Now this will this is also next. This will imply arrow step. So but now remember beta is unique. This beta is working. This is what we are requiring. Okay. We got one beta which satisfies this condition, this equality condition. And because such a beta is unique, which represents f, that is why this is the unique choice we have. So we got 3 by 2 in first coordinate. So these two are wrong. 4 by 3 in second coordinate and 1 by 4 in last. This is correct. Okay. So if you understood, I'm waiting for a minute. If you don't understood, you can ask.
Sir, please rewind the theory about this question.
Okay. So this was this follows from representation theorem. Representation. Which says every inner product, sorry, every linear functional can be represented by elements of V. Something like you have representation theorems which says uh, this V and V duals, if you remember, these are isomorphic if V is finite dimensional, right? If V is finite dimensional, then V and V dual means these are what is V dual? These are what are elements here? Linear functionals, okay, on V. These are maps from V. These are collection of maps from V to A. Means if field is F, let me write it there. And what is this? Here we have elements of V. So this isomorphism there, it it was not a general isomorphism. Okay, it was given by taking dual basis and that. This is this is something similar going on here. That every element here F goes to some element V here, and some element goes to F here. It's the same here happening. So any linear function F is representing some element beta, and if you have an element beta, then send it to this inner product. This is your linear function. So this is kind of isomorphism between duals of vector space, means V and V star. Okay, so how we get this is from representation theorem that I'm not going to recall it for you. You can watch lecture once more if you wish. So this theorem, this is what this theorem, representation theorem. Any linear functional f, any linear functional, then there exists beta, such that f alpha can be written as taking inner product with beta of alpha. So that is what is happening here. So nice that you asked this question, and I suppose you understood. If not, you
Yes,
can
sir.
watch
Thank
this part. This is one-to-one correspondence between linear functionals on V and elements of V. Okay. So let's see next question. You have matrix representation for linear transformation E R2 to R2. Okay. Standard ordered basis के respect में है. Then we want to calculate adjoint of T means E star. So let's first calculate matrix of T star. What is this matrix of T star with standard basis? This is nothing but if you have matrix of T, take conjugate of it. Conjugate means this means first take transpose and then complex conjugate it. So what it is? 1 I 1. Okay. Now conjugate it. But what it is? If you take transpose, nothing is happening, right? Yeah. If you take transposition, nothing happens. Sorry, transpose. Then if conjugate may we got some changes. It becomes minus I. I becomes minus I. Okay. This is your matrix representation for T star. Now T star applying on XY. This is just given by matrix 1 minus I 1 applied on XY. We get I'm writing in column notation, but you understood this. X minus IY minus IX plus Y. So X minus IY. So these two options are wrong. So now in the second coordinate, hello, am I audible?
Yes, sir.
Thanks. So in the second chord we want, so we are taking I common. So let's say minus I common, then what it is? Minus I common, then it is X and in the second coordinate we should get I y. And, minus I into I becomes plus 1, right? So here we have 1, hidden 1. So this is correct. So we are taking minus I common. So first option is correct. Okay. Okay. Understood? This was simple. Little calculation to match your answer. I had a doubt. Can such a matrix from R2 to R2, how this kind of representation where I is appearing?
Yes, sir. I have also this doubt because here given that field is real.
Yeah. So I think constant should be from the field. So replace everywhere by C or clear understanding. Okay. The field is C. Take it is equal to C. So now it is correct. Okay. I'm leaving
I
this
have a
now.
doubt, sir. What
What?
is the requirement of replacing R square by C square? I mean R2 to C2. If we replace only field by C, then what's problem?
So you want two-dimensional space, right? Then only you will get 2 cross 2 matrix. This is
Yes,
why we are. So
the
that is why
given
I'm
matrix
taking.
is the given matrix is also 2 cross 2.
No, no. If you take your vector space just let's say C, then it is incorrect.
Why?
Then you will get 1 cross 1 matrix, right? So you should take two-dimensional vector space so that you'll get 2 cross 2 matrix.
Okay.
So if you have, let's say, I'm just writing here R n to Rm some t, okay, then you get P and in the matrix representation with some basis, let's say beta 1, beta 2, is some matrix A, order is M cross N.
Here
Okay,
field is R.
I'm just writing you and F U, anything, any field. If your first vector space is n dimensional and second is m dimensional, then your matrix representation has this order m cross n. Okay,
Okay.
look back the matrix representation part
I have
as well. It is
another doubt.
part.
What is the dimension of R2 over C? I think it's 1.
R2 is not a vector space over C. Okay,
Okay.
why? Multiply by I in this vector 1 1.
Yes, yes. Scalar multiplication is not closed.
Correct. Yes. So this is now correct if you replace everywhere I'm saying R by C. Okay. So
Okay,
let's see
thank
next
you.
question. Next question. V be a finite dimensional inner product space, then which of the following statement is correct? V be orthogonal projection onto W, then E is equal to E star. Okay. This is the last corollary of proposition in this V, and in the class it was proved. Okay. See here. Oh, I should do it. At that time, I was thinking, I can leave this. I will do in the question. Okay, not here. E is equal to E star. Let's see. Sixth question. Sorry. Huh. How to do it? Yeah, I don't have anything much. Okay. Now, we want to calculate uh, E star is equal to E. So, E alpha beta is equal to, if we prove E alpha is equal to alpha E beta, this will imply for every alpha beta, this will imply E star is equal to E. Okay, because the operator which is hidden here, that is called E star. So, so we need to prove E alpha beta is equal to alpha E beta. Let's see how to prove it. In place of, let's say we are starting from right side, alpha E beta, then alpha can be written as I minus E alpha plus E alpha. So E alpha get cancelled, then I alpha is just alpha in the first coordinate, and in the second coordinate we get I minus E of beta. Okay. We need plus here. Okay, sorry, not like that. I beta first minus this. Let me rewrite it. What I need here. We need just E beta so that it is not cancelled, but I'm writing it differently. It minus here. Okay. I minus B E. Okay. Now it is correct. Now it is E beta itself. I beta get cancelled. Now expand this. Okay. Expand it. So what is left is this part. E alpha and this side I beta. This part is only left. Everything else is cancelled. Let's see why it is. So I minus E alpha with I beta plus uh, no minus here I minus E alpha with I minus beta I minus E beta minus again E alpha I minus E alpha sorry beta. So Anyway, this was done in the class, but I think this is only left. This is 0 because this belongs to W and this belongs to W complement. Okay. How about this? Okay, take these two parts together. This is anyway 0, this last part. So what about this? I'm saying this is 0. How? Take this like I minus alpha, E alpha in the first coordinate, and in the second coordinate I beta minus I minus E beta. This is equal to this. What it is? This is I minus E applied to alpha, and this is just E beta. Now this belongs to W complement, and this belongs to W. These were orthogonal projections, so this is 0. So what left is this part only, E alpha and just beta here. I beta is beta. So this is how it is proved. E is equal to E star. Okay, so this is little calculation you can do by yourself so that you can practice what is happening. The main thing to remember is this: E, whenever you have E any V and I minus E any W or any V prime, let's say, this will become 0 just because this is orthogonal projection on W and this is on projection on W complement. That is why. So first part is correct. E is orthogonal projection and I minus E is I minus E star. Oh, so this follows from A. It's adjoint is itself. Why? Means I minus E is also a um, also an orthogonal projection. But some different subspace that does not matter. But it is also a orthogonal projection on W quadrant. So B is also correct. Now all about let's go for C. For all linear functional f on V, there is a beta element of V which represents f. This is correct. Representation theorem. So this is this is also correct. Part C. Okay. This is just theorem. What about D part? This is this should be for finite dimensional space. This is correct. And if it is a basis, right? This is Pythagoras theorem in that case. Generalized Pythagoras theorem. But it is incorrect if it is infinite dimensional space or this is incomplete set of orthogonal or orthonormal elements. Okay. I'm just saying if it is it can be this orthogonal, we have such orthogonal extension into higher dimension, then this is incorrect. Let's see for one. For example, for V I'm writing V is equal to let's say R3 and take 100 and 010. This is your that collection alpha 1 alpha 2. And projection onto this subspace, let's say this and subspace xy plane, then this quantity and take some element, let's say 1, 1, 1 belonging to R3. This is your beta, and beta in alpha 1 direction, alpha 1 square, not write sum here, directly write it, beta alpha 2 direction, and make it mod alpha 2 square. Uh, is this equal mod beta square? No, no, right? Because this set can be extended to a higher orthonormal set. So you get here this part, you get 3. This part you get just 1 and 1 here only. Oh, sorry. There is a little mistake here. Square of this. So let me write it once more. Little mistakes. Network issues. Okay. So if you have just 3 coordinates and project and then take is where is in the question? We have this just the length of the projection. Okay. So you get 1, 1, 1 here and in E1 direction and mod of this. And mod E1 square is just 1, so I'm not writing that. So now in this direction 1, 1, 1, in E2 direction, this projection and the length of this. Now they are taking square of this, right? Square. So is this equal norm beta square? This inner product is what? Such 1. Right? This inner product is again 1 square. Question mark is here. And beta norm beta square is just inner product of beta with itself, and it is 1 plus 1 plus 1. This is 3. This is not equal. It will be equal if it is orthogonal basis. It says okay. So if you miss some edge in Pythagoras theorem, then you will get lesser. So this inequality. And it is correct. Inequality, yes, but not equal. Not not necessarily. So we get this is wrong. This and I was just giving you counter example for that. So let me know if you understood this. Let's say next question. Is given by this. So every question is all about R2. Sorry, R3. Standard inner product we have. Okay. Sorry. Let's see first of all matrix representation of P, and then we'll go for T star. So matrix representation of P with standard order basis. This is 1, 1 0 here, 1 0 1 here. I'm wrong. You know, second row should be 0 1 1. So I'm writing so fast matrix representation. You can also write it. How? Because a standard basis is too trivial, right? Just how one in one coordinate everywhere 0, 0 1 0, something like this. And if you calculate T of E1, this is your E1, this is E2, E3 0 0 1. T of E1 is just first column, and that is coming out 1 0 1. This first column. Calculate from here. T of E2 is what? You put just y is equal to 1 everywhere 0. This is 1 1 0, second column. T of E3 is just 0 1 1. That is equal to 1 and x y is equal to 0. So this is your T. So what about T star then? I just uh, solved similar question where I just wrote T of B and then take conjugate of it. Means conjugate and transpose. So let's do one by one. First, let's do transpose. First row becomes first column. 0 1 1 1 0 1. Last row becomes last column. Now, what about conjugate? Because this is real matrix, complex conjugate is itself. So this is your T star. Now T star of 3 5 2. So T star of 3 5 2. This can be calculated by this matrix only. Matrix you got for this 1 0 1 1 1 0 0 1 1. Lie on 3 5 2. You get 3 plus 2 in first coordinate, 3 plus 5 in second coordinate, 5 plus 2 first coordinate. This is 5 8 7. Yes. So which option is correct? Option number 8. Understood. In this question, main thing to remember is this formula only. That matrix representation for T star is nothing but star of matrix representation. Uh, this star means transpose and conjugate. So I think you understood this because this is very simple. So let's see next question. Question number 8. We have this basis. This is not a standard basis, but we have a standard inner product. Okay. We have enough time, I think. So let me explain this inner product is what x1, x2, x3. If you have first vector and you have second vector y1, y2, y3, then inner product is standard inner product x1, y1 plus x2, y2 plus x3, y3. So you have basis and G matrix is defined But if you see here, because all elements are real elements, I mean real number, so this is also equal to alpha j alpha k. So, it will help in writing equation. Let's see how G is given. Matrix representation of G. So let's say this is your x1, this is x2, this is x3. So first you take x1 with x1, x1 with x2, x1. G matrix is given by this kind of formulas, right? X1, x3. But this is symmetric matrix. Because of this, Gij is equal to Dji. So this is again x1, x2. This is just x2, 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 x3. This is x3, sorry, x1, x3. Because of similarity, these two are equal. X2, x3, x3, x3. So from here itself, C is clear that G is symmetric, and D is also clear. Symmetric matrices are diagonal. Symmetric real matrices are diagonalizable. So you can read about it from somewhere. I'm not going to explain. Remember, the symmetric matrices are diagonalizable. This is fact. So let's see explicitly what it is. X1 with x1. Someone tell me what is inner product of x1 with x1?
1.
Nice. What about second entry here? X1, x2? 1 itself. About 3? Third coordinate? Third entry should be also 1. So because it is symmetric, we have this type. What about x2, 2? X2, x2? 2, right? 1 plus 1. But here also we get just 2.
It is 2
1.
or root 2. Inner product root under x1 square plus x2 square.
No, 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 no. Norm of V, square was, this was defined as under root VB, right?
Oh,
While
okay,
taking
okay.
while taking inner products, you don't take under root. Otherwise, that will be the norm of it. But norm of V works only if you have first and second coordinates same, like VV here. Okay, then only you get this quantity positive. Then you can take in square root. So let's say what about this? Because symmetricity, you get 2 here. What about x3 with x3 inner product? You get 3, 1 plus 1 plus. Is this invertible? Now you have to check invertibility of this matrix. So you just take, if you calculate determinant, that will be nice, right? Determinant of G. If it is non-zero, you are done. Let's calculate 1, 2 into 3, 6 minus 4 minus 1. I'm expanding along first row. 3 minus 2 plus 2 minus 2. So you get 2 here minus 1 here and plus 0 here. You get 1. which is non-zero. So it is invertible. So B option is also correct. Now once B option is correct, A option is wrong. Why? If G is invertible, G is 1 1 onto linear transformation. Right? So only 0 goes to 0. Nothing else goes to 0. You have invertible linear transformation. That means you get isomorphism. And that is 1 1 onto and homomorphism. Means linear transformation. 1 1 will imply that only 0 goes to 0. So something which is non-zero cannot go to 0. So that is why it is incorrect.
Could you please explain option D? Why it is not diagnosable?
And what I am missing this. Okay. Symmetric matrices, symmetric real matrices basically,
Oh, okay, okay, okay.
they are diagonal. Then explained here. You can read it about it from somewhere. It is given in books.
Okay, okay, it's okay.
Okay. So, but there is mistake in the question. All options are incorrect. What I wrote is incorrect. Why? Can someone tell? All option which I'm saying correct is incorrect, and I'm saying incorrect, they are correct. If you do like this, you'll get just 0 marks. You know why? Question is all asking what are incorrect statements. Incorrect. So let me use another color, maybe blue color, because of this. We should get this to be correct, this to be correct, and these two are incorrect. Okay. Blue pen is just to correct things so that when you read it, so this kind of mistakes happen in the exam. Yeah, when I was, let me share a little story. I was sitting for exam, IIT jam. Okay. And this kind of mistakes happen in 2 3 question, and after that I was completely sad. Okay, so let me go to next question. Don't do mistakes like this. These are Let's see next question. Ninth question. Okay, so here you have same basis. Okay, same basis we have. Oh, standard product we have again. Standard product on R3. V is also same in last question. And G is this matrix which is defined by, oh, this is same ijth entries alpha I inner product of alpha and alpha. Okay. Then which of the following is are correct? Now, now you tell me if you remember. This was correct option, and we also calculated determinant, right? Follows follows from question 8. no need to explain, right? We did this long calculation here. Determinant is equal to 1, and the matrix is given by this 1, 1, 1 in first row, first column. Second is kind of 2, 2, 2. So let's see last question. 10th question. WB finite dimensional with subspace of inner product space V, and E be the orthogonal projection of V on W. Then the power star denotes adjoint operator, corresponding operator, adjoint. Then for every alpha beta, which of the statement are are correct? So sorry, incorrect. We have to check which are incorrect or is incorrect. Let's see. First of all, by definition, we have E alpha beta is defined as alpha E star beta from definition of E star. So no option like this. So this is just definition. I'm just recalling. And E is the orthogonal projection. Okay. Now you should remember this thing, that E star is equal to E. From which question? I solved this in A. From question 6, part A. E star is equal to E. This was also done in the classroom, so uh, you can. I'm just giving a reference from what we just did in question number 6. So this is correct. Now from definition and from 3, this is from 6A, and this is from definition of E star plus 3 below will imply this. Okay, you just, this is just in place written E star. So just from the definition, this is correct. Okay, so about others, what about part 4? We'll go to part A after some time, means after doing part 4. Let's do it. Just little calculation. E alpha and beta can be written in. Okay, let me write it once more. This is explanation part 4. Uh, in place of beta, we write something else. Let's write E alpha uh, I minus E beta plus E beta. Okay, this is just I beta and which is just beta. So now expand this. This is comma, not alpha. E alpha, comma, I minus E beta plus E alpha, E beta. But you see, this is 0 now because this belongs to W and this belongs to W complement. That is why it is 0. So 4 option is correct. Then E is projection on W, orthogonal projection. I minus E is orthogonal projection on W complement. So they are in the complement, orthogonal complements. That is why inner product of them is 0. So we have these three options correct. What about A? Oh, sorry, we are choosing again correct option only. So
Sir, but in question incorrect. We need to choose incorrect.
yeah, let me choose incorrect after some time. Okay, doing mistakes again. Anyway, so what about A? First option. Is that correct or no?
Excuse me, sir.
Yes,
Oh, given option 2, this is relation is true or false?
it's true. This relation is true because E star is replaced by E in this definition.
Oh, okay.
When you these two things will imply second. Okay, what about first option? Let's see. Alpha can be written as I minus E of alpha plus E alpha. This is your alpha. And in the second coordinate, we have E beta. Then this is equal to just E beta. Sorry, sorry. E alpha, E beta. And this side it was equal to alpha E beta. Now from 2 maybe this is equal to, I mean this equal to is transitive, so you can write anywhere E alpha and beta. These kind of relations we have E alpha E beta, E alpha beta, E alpha E beta. These are all equal, but I think I minus E is not working here. So first option is incorrect. Okay, from calculating E throughout, we are not getting any relation. It just contains I minus E alpha in first quadrant. Let's see. Let me try once more if it is correct. So we'll get something out of it. So in first place we have alpha. So I minus E alpha plus E alpha. In the second coordinate we want beta. We want beta here. In the first we want I minus E alpha. Second we want beta. So we want beta here. So but we have E beta. So we are wishing to get beta. So beta. Okay. I minus E beta plus E beta. This is your first beta here. This is your alpha E beta. Can be written like this. Okay. Then uh, we were wishing, sorry, comma is in. We were wishing to get I beta here so that we are left with beta. But that is not we are getting. So after all this calculation, you will be left with E alpha, E beta, in the first, and in the second you have I minus E alpha, comma, I minus E beta. That is what is left, and everything else is zero because of orthogonal projection. So first option is incorrect. Okay. Um, if someone says that it is correct, please prove for me. Okay. I think it is incorrect. So if at all there is a correct option, it should be incorrect. So let me again write it. Because of this incorrectness, this is your correct option. Everything else is false option. I mean, I'm just taking another color to clarify that because of this, we want incorrect statement only. So the correct choice that we should take is first option. If at all there is a correct option, first should be a correct option because everything else is correct. This is correct. This is correct. Remember this. I mean, I'm not saying remember this, but I'm saying explanation is given in this side box, and two follows from these two definition and this. So if you have more doubts, you can ask.
Sir, could you please tell about the book in which the practice questions are given?
Uh, Actually, I have given a book like I was saying. Which book? Hilbert Stein. Is there a linear algebra by Hilbert Stein? Let me search. That book was so nice. I think, well, so much of matrix representations and many exercises are there. To practice, that is the book, best book, I think. Hilbert Stein, linear algebra. Yeah, there is Introduction to Linear Algebra. Okay, he's a very good
Sir,
speaker. He
please tell me your email ID, sir.
okay. I'm writing here. If you are looking, note it down.
Excuse me,
Yes.
please repeat the writer name.
Okay, let me write in some other color. Red color. Okay. First of all, my email address is ans.math at the rate gmail.com. And the author I was mentioning, that name is Will Gilbert Stein. Introduction to Linear Algebra. So this is the book name. Okay, so this is almost time, I think. We have more 10 minutes. If you want to ask question, stay. You can stay and ask, or we can leave.
If E is a projection operator,
Yes.
then can we write E is equal to e to the power n? N goes to 1, 2, 3, dot, dot.
Yes. Because if it is projection operator, E square is equal to E. Now you multiply each time. Same identity will hold. That if E take any power of E, it will be E.
Okay.
You can simply think like this. E composite E is equal to E. This will imply compose E both side again. Then you get 3 here and 2 here. But use this formula again. E square is E. So by induction, this will be like if any power n is equal to E. Okay, so we'll meet next week again. And I think there is an extra class I have to take for 1 hour. I don't know what to explain there because I'll explain something from linear algebra. Okay, they will announce the date by the email. So you can join there. Class is over for today. See you next week. Bye bye.